Alright, this mini lecture is going to be on atoms and moles and the interrelationship between the two. Alright, a mole is nothing more than a fancy name for 6.02 times 10 to the 23rd. 1 mole is equal to 6.022, that's the 4 significant figures, times 10 to the 23rd. So you can have a mole of pennies, and that means you have 6.022 times 10 to the 23rd pennies. You could have a mole of automobiles, and that means you have 6.022 times 10 to the 23rd automobiles. The word mole to a chemist is nothing more than, for most people, when they say they have 12 eggs, they don't say I have 12 eggs, they say they have a dozen. So 1 dozen is 12. So we have a word that represents a numerical value. Alright. So if we can find the mass of a particular number of atoms, we can use this information to convert the mass of an element sample into the number of atoms of that sample. And you say, well, why would I want to do that? Why would I want to convert mass to number of atoms? Well, it's kind of like this. If I want to combine sodium ions with chlorine ions to make table salt, NaCl, well, it's not about how much sodium weighs and how much chlorine weighs. I have to have 1 atom of sodium or 1 ion of sodium for every 1 ion of chlorine. If I don't have one of these ions, I cannot make the product sodium chloride. But from a mass perspective, sodium weighs 22.99 AMUs, or atomic mass units, and chlorine weighs 35.45 atomic mass units. Now those are, I've got those numbers from the periodic table. So it takes more chlorine to make a mole, or let's say it this way, 1 mole of chlorine is going to weigh more than 1 mole of sodium. So it's going to require more mass of chlorine than sodium to have a 1-to-1 relationship, so that I've got enough sodium ions to combine with enough chlorine ions to totally consume those 2 ions. And I think that'll become apparent when we do some more problems here. Alright, let me erase this up here so you can read that, and let me erase this before some other writing comes up. Alright. So, pretty much what we've said, 1 mole is equal to Avogadro's number of things. Alright, let's move on to the next slide. So, how are we going to use a mole? Well, it says calculate the number of atoms in 2.45 moles of copper. So here they've given us a quantity of copper. Now, remember what this means. It means that you have 2.45 moles, just like when we say, if we have 12 dozen eggs, 12 dozen eggs can be broken down into, meaning I have 144 eggs. 12 times a dozen, which is 12. 12 times 12 is 144. So when I have 2.45 moles of copper, that tells me that I have 2.45 times Avogadro's number, 6.022 times 10 to the 23rd. Alright, so let's look at this problem. You start off with what's given, 2.45 moles of copper. You're asked to find the number of atoms of copper. Okay, here's the conceptual plan. We want to convert moles to atoms. Now, in order for us to convert moles to atoms, you have to know the relationship between moles and atoms, and that is 1 mole is equal to Avogadro's number. That's what this is. Instead of saying 6.022 times 10 to the 23rd, we just say Avogadro's number. Some people say Avogadro's number. All right. So this is just like the math we did in chapter 1. This is an equality. From this equality, you make a conversion factor. Now we're trying to go from moles to atoms, so we know that in our conversion factor, we're going to need moles in the denominator and atoms in the numerator. So that tells us that we will divide both sides of our equality here by 1 mole. And that will be our conversion factor. All right, let's see what goes on here. All right, well, that's what they did. There's the relationship, or the conversion factor. So we know we've set this up right because the moles of copper will cancel out, and that we'll be left with atoms of copper. And to check our answer, we would expect this to be a large number. Now here's another check. Here's another check to make sure you know you're on the right track. You have 2.45 moles of copper. You know that 1 mole is Avogadro's number. So we have more than twice that. So we would expect this number to be at least 1.2 times 10 to the 24th. So if this number is larger than 1.2 times 10 to the 24th, well, that makes sense because we have a little bit more than 2 moles of copper. So that's a way to check to make sure you're on the right track. All right, let's do this one. In this problem, we're doing the reverse. In this problem, they give us the atoms of silver, and they're asking you how many moles of silver are in the ring. All right, so you write down what's given. 1.1 times 10 to the 22nd atoms of silver. This is the chemical symbol for silver. You're asked to find the moles of silver. So the plan's going to be start with what's given and convert to what you're trying to find. Atoms to moles. The relationship is the same. 1 mole equals Avogadro's number. The difference on this problem, we want atoms in the denominator and we want moles in the numerator. So instead of dividing both sides by 1 mole, we're going to divide both sides by Avogadro's number. All right, this side becomes 1. That tells me this is a true conversion factor. And that's the conversion factor I'm going to use in order to solve this problem. And I'll probably erase it here. There it is. Well, let's erase this so you can see the conversion factor. There it is. All right. We know we set this up right. We look at it, calculate it out here. Atoms in the numerator, atoms in the denominator, and those atoms cancel out. I'm left with moles. There's my answer in moles. And then here's my answer to the correct number of significant figures too, because we only had 2 significant figures in this number. Now, here's how to check your answer. 1.1 times 10 to the 22nd silver atoms is less than Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd. So we better have less than 1 mole of silver, and we do. So think of moles as like little units, like 1 dozen eggs is 12. 12 dozen eggs is 12 units of 12, which is 144. So moles are ways of packaging atoms together, or molecules together, or compounds together, or whatever you want to pack together of the order of 6.022 times 10 to the 23rd of them. And you say, well, why do we use that in chemistry? Well, when we deal with that amount of atoms, molecules, compounds, it's a quantity that we can see, that we can pick up, that we can manipulate, that we can weigh on a balance. That's why we generally work with moles. Nobody wants to keep saying, just like on the lecture yesterday, nobody wants to keep saying things like 6.022 times 10 to the 23rd or some multiple of that. Just like with atomic mass, we don't like to say, well, a proton, 1.67 times 10 to the negative 24th grams. We normalize or make relative the masses to carbon-12 so we don't have to keep saying those exponential notations. Well, the mole does the same thing for us. And why the mole is so important, again, is because all the atoms on the periodic table all the elements on the periodic table weigh different amounts. And it's not about the mass or quantity that you have when you're doing a chemical reaction. It's, is there one atom to react with another atom? Alright, so on this slide, what's very important is we defined yesterday that one atom carbon-12 weighs exactly 12 atomic mass units. But here's the big one. 1 mole of carbon-12 weighs exactly 12 grams. You say, what's the implication of that? Think about it. What would be the implication that it weighs the number is the same here, all that's changed is the unit? Well, that's a big advantage for us, because what that does is all the atomic masses that we've been talking about on the periodic table in AMUs now can be thought of in terms of grams. So if you have one atom of carbon-12, it weighs exactly 12 AMUs, 12 atomic mass units. But if you have 1 mole of carbon-12, it weighs exactly 12 grams. Alright, so the mass on the periodic table of carbon, somebody asked this the other day in class, we said that carbon-12 weighs exactly 12 grams, but if you look on the periodic table, we said 1 atom of carbon-12 weighs exactly 12 atomic mass units. And now we can say 1 mole of carbon-12 weighs exactly 12 grams. But when you look on the periodic table, it's 12.011. Why is that? Remember, it's an average of the isotopes of carbon times the masses of those isotopes times their abundance. And it is an average, so keep that in mind. But again, the whole reason why this was important, this slide, is that all of the atomic masses can now be thought of in terms of grams if you have a molar quantity of that substance. What's that going to do for us? It's going to allow us to calculate number of atoms in a particular mass of an element. Okay? Know this term. This is one of the most important terms in chemistry, molar mass. The mass of 1 mole of atoms is called molar mass. Molar mass of an element in grams numerically equal to the element's atomic mass. So that means we can just look on the periodic table and get the molar masses. The lighter the atom, the less a mole weighs. That makes sense. The lighter the atom, the more atoms that are in 1 gram. That's what I was saying previously. If we're looking at sodium ions and chloride ions, chloride weighs more, so you don't need as many. You'll need less atoms to get to 1 gram than you would for sodium. All right, so here we go. This chart shows that 1 atom of hydrogen weighs 1.008 atomic mass units. If you have 1 mole of hydrogen, you have this many atoms of hydrogen. And now 1 mole of hydrogen weighs the exact same number, but it's the units that's changed. It's grams. And a gram's a lot heavier than an atomic mass unit. So the number is the same, the unit is different, and that quantity is different. A gram is much heavier than an atomic mass unit. Remember, 1 proton weighed 1.67 times 10 to the negative 24th grams. So that's how much actual hydrogen weighs, hydrogen 1. But here we're saying it's 1.008 grams per mole of atoms. But what's nice is you can see these on the periodic table. Nothing's changing as far as the number. It's just remember, if it's 1 atom, it's AMUs. If it's a mole of atoms, it's grams. And again, what this is showing is molar quantities are a quantity that we can actually manipulate and see, whereas we can't see an atom.